Okay, Newton's laws today. This is the biggest section of Unit 3, so it'll take us a little while, but it's not a terrible one. So let's get right after it here. So we're talking about Newton's laws of motion. There's Isaac Newton. Check out that guy. He's a nice looking dude, sweet hair. Moving on. Okay, so Newton's 3 laws. First one was the law of inertia, Newton's first law, which says an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an unbalanced force. All right, so if an object in motion tends to stay in motion, why don't objects keep moving on forever? Well, things don't keep moving forever because there's always an unbalanced force acting upon them. There's gravity pulling down, there's friction, there's always some other force moving on. If you get out in space, maybe that's where you run into a place where there's less and less opposite force, but even then, there's gravity of objects that would cause the change in direction of an object. Okay, a book sliding across a table slows down and stops because of force of friction. If you throw a ball upwards, it will eventually slow down and fall because of gravity. So that moves us to inertia. Inertia is a property of an object that describes how much it will resist a change to the motion of the object. More mass means more inertia. Okay, so if you think about when say you're playing football, a football athlete wants to have more mass to them, because if you get that mass moving, it causes more work to cause a change in their motion. So inertia, according to Bill Nye, inertia is a property of matter, and it's the property of resisting a change in motion. So in this would-be animation that's not playing, the car's going to drive up and hit the wall. What do you think happens to the guy when he hits the wall? He has motion moving in this direction. Car hits the wall, car stops, the guy keeps going. That's inertia. Okay, on to Newton's second law. Newton's second law says force equals mass times acceleration. So here's our mathematical formula. There's force, mass times acceleration. There it is again, force, mass times acceleration. The force is measured in newtons, which technically is a kilogram meter per second. So a newton is the amount of force that it takes to move 1 kilogram, 1 meter per second. Okay, acceleration of gravity of the earth is 9.8 meters per second. You're going to need to know that. That will be something we'll use. And so weight is the force, mass times gravity of the earth. Weight is the pull of gravity coming down. Okay, so weight is the measure of the force of gravity on the mass of an object measured in newtons. Mass is the measurement of matter in the object. It's measured in kilograms. We talked about this in an earlier video. If you were to travel to the moon, your mass would not change, but your weight would, because the gravity on the moon is less than the gravity on Earth. Okay, so here, one rock weighs 5 kilograms, the other rock weighs 0.5 kilograms. How much more force would be required to accelerate the rock at the same rate as a second rock? We need about 10 times as much force. All right, let's move on. Newton's third law, every action there's an equal and opposite reaction, or every force there's an equal and opposite force is another way to say it. So in this case, we've seen this before when we talked about forces and things like that. For every action, there's an equal and opposite reaction. The force pulling down on the book is gravity. The table is pushing up with an equal force on the book, so the book does not move. Okay, think about this. What happens if you're standing on a skateboard or a slippery floor and you push against the wall? You slide in the opposite direction. Because you pushed against the wall pushed back on you with an equal and opposite force. There just wasn't a lot of friction underneath you when you're sliding. Okay, why does it hurt so much when you stub your toe? Your toe exerts a force on the rock exerts an equal and opposite force back on your toe. The harder you hit the toe against it, the more force the rock exerts back on your toe, the more your toe hurts. Okay, another one. A bug with a mass of 5 grams flies into a windshield of a moving 1,000 kilogram bus. Which will have more force, the bug on the bus or the bus on the bug? Okay, well, here's how we can look at this mathematically. First of all, a sweet picture of a squash bug, but force would be the same, but it would go like this. The force of the bug has a small mass, but has a large acceleration. Remember, when two forces are going opposite direction, you have to multiply the acceleration. So the bus is coming in one direction, and the bug is coming in the other direction. So their acceleration is added together. So the bug has a large acceleration. Relatively speaking, the force of the bus has a large mass, but has a relatively small acceleration. Okay, so they would be an equal force. Okay, and so then consider hitting a baseball with a bat. If you call the force applied to the ball by the bat the action force, what's the reaction force? Is it the force applied to the bat by the hands? Is it the force applied to the bat by the ball? Is it the force the ball carries when it's in flight? Or is it the centrifugal force of the swing? Okay, are you thinking about it? Are you playing the Jeopardy song in your head? Do, 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 do. That's enough. I'm not doing that anymore. Let's do the last part. Do, 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 do. Okay, so hopefully you wagered enough money that's going to help you win. The answer to this question is, oops, B, the force applied to the bat by the ball. Okay, so the ball has a force, the bat has a force, they're equal and opposite. Ball goes flying. And Newton's third law. So how about this one? Suppose you're taking a spacewalk near a space shuttle and your safety line breaks. How would you get back to the shuttle? Okay, so the thing to do would be take one of the tools from your tool belt and throw it as hard as you can directly away from the shuttle. Then with the help of Newton's second and third laws, you will accelerate back towards the shuttle as you throw the tool. You push against it, causing it to accelerate. At the same time, the Newton's third law is the tool is pushing back against you in the opposite direction, which causes you to accelerate back to the shuttle as you hoped. So your best bet would be to pick up your heaviest tool and push it away from you. And there we go. That's the end of this one. Nice job. You made it through lesson 3-6. Thank you for listening. Bye.